This video presents the Raster Storage Archive and its query engine. A number of topics will be covered. Some background information explaining the need for the RSA, the design of the storage system, usage of the RSA, and usage of the query engine. Geospatial data comes from many sources: satellites, LiDAR, and aerial photography, to name a few. Even a single source can produce data that is difficult to consume. For example, the Landsat satellites produce data in chunks called scenes that take effort to browse through. A user would need to search for the scenes that occupy a region of interest, download them, and then open them together to view the data. Even then, the image files would overlap, which has to be managed by the user, viewing application and processing tools. The RSA is a storage system for geospatial data that simplifies data access. Datasets are stored in a way that allows them to be opened as one large image while ensuring efficient read-write access to small regions. With the RSA, data can be accessed as a contiguous image just by providing the region of interest as a bounding box. This greatly simplifies the task of extracting data from the data store. The Raster Storage Archive currently handles data with 3 dimensions: time, y, and x, and any number of bands. A band is a channel of data such as red, infrared, elevation, or population. Data is stored in buckets called datasets, which are used to logically group the data. For example, you might have a dataset called Landsat 7 or Digital Elevation Map. Raster data is not stored in a relational database. Instead, it is stored as files in a regular file system. This minimizes overhead for data extraction and allows it to be directly accessed by tools other than the RSA. Datasets in the RSA can be very large, on the order of several terabytes. It would be impractical to store the dataset as a single file, because merging and updating data might require very large portions of the file to be rewritten. Therefore, the RSA automatically splits data into chunks called tiles during import. Each tile is 2-dimensional, varying only in space. Additional tiles are stored for data that varies through time. The RSA aggregates the tiles into seamless 3-dimensional images when the data is accessed. In addition to making management of the data easier for the RSA, it also means that the dataset may be sparse. It is okay for data to be missing for a certain time, place, and band, in which case the file will simply not be present in the storage pool. The RSA is built on well-known and robust open-source libraries, such as GDAL and NetCDF Java for image warping and I/O. OGC-compliant web services are provided by Threads. The RSA can be run on a personal computer, but it excels when run on a server. In addition to facilitating file sharing, this allows queries to be sent to the data store, with only the result, which may be a much smaller amount of data, sent back to the user. The command line and web service interfaces make it ideal for automation. The RSA can even recommend how to split up large queries for faster execution on high-performance computers. Let's have a look at the RSA command line client. The first thing we'll do is create a dataset. Then we'll add a band of data called band 3 and create a single time slice for the 16th of January 2010. Now we can import some satellite data into the band. The dataset has now been populated. We can query the RSA for basic metadata. It shows the data extents, image size, and storage location. These are the contents of the storage pool. The directory structure is kept simple, so you can access the files directly if you like. You can ask the RSA to show metadata using the format of the Common Data Model, as used by NetCDF. Data can be exported to be viewed offline. Like most of the features of the RSA, this can also be done using the web services. If you have access to the server, you can view the live data as a single contiguous image without exporting it. The RSA will create an aggregate view of the tiles as NCML. This can be opened using standard NetCDF utilities such as Tools UI. Data being viewed, exported or queried can be constrained in time and space. Here we specify spatial extents to view a single tile. This is handy when you want to inspect a small portion of the dataset. The Raster Storage Archive provides a system for querying data on the server. Queries allow a user to ask complex questions such as, which areas were wet in the first quarter of 2012? And, where are there gum trees at altitudes greater than 1,000 meters? This image shows the output of the water query. On the left is the input image. The right image shows lakes and rivers identified using the query engine. The input is a three-dimensional Landsat dataset, but only a single time slice is shown here. The output is two-dimensional. At its core, the query engine is an image processing system for NetCDF data. The engine itself is not tied to the RSA. It is quite general purpose, and the RSA makes use of it as a library. RSA query allows users to define filters that transform image data and queries that link filters to specific datasets. Filters can be chained together to form more complex queries, like pipelines or workflows in other applications. Developers write filter kernels that perform operations on the data, such as add, divide, etc. The query engine abstracts away other image processing details. It takes care of dataset alignment, pixel iteration, I/O, and memory management. Importantly, it abstracts away the tiled storage of the RSA and provides a unified coordinate system. It can operate on multi-band 2D and 3D data and perform dimensional reduction, for example, removal of the time dimension to summarize data. Queries are defined using XML, and filters are written as reusable Java classes using a special API. The query engine is designed to have a clean separation between these two components. Specialist programmers can write filters in Java. These can then be mixed and reused in queries by other members of the team. The API has a comprehensive type system which allows filters to be type agnostic, to the point that they often do not need to know if the data is scalar or vector, that is, single band or multiband. This is the user interface for the query engine running in a web browser. On the left is the toolbox. It shows all of the input datasets that are available and the filters that can be run on them. This is an input dataset, this is an output, and this is a filter. This is a pass-through filter. It simply copies data from the input, in this case band 3, to the output. We can run this query by pressing the snapshot button. The filter has been run on a small section of this dataset, and this is the output. There are 3 time slices visible. The second is mostly empty. There was probably a cloud here which has been masked out. All 3 times are over the same location. The query engine automatically configures the dimensionality and data types of the output, although it's possible to override the types. This is a blur filter. Let's run it together with the original filter. Now the output contains 2 bands, one of which has been blurred. Notice that the filter preserves no data values. The transparent regions have not been blurred. Suppose we wanted to find all locations that were wet. To do this, we can take band 5, which is infrared, and run it through a less than filter. When this band has a value of less than 1000, it probably indicates the presence of water. The output now shows which areas were wet for each time slice. However, what we really want is to see a summary of which areas were wet over all available times. To do this, we can use a reduction filter. These are special filters that reduce the dimensionality of the data. This is a maximize filter. For each pixel in the output, it walks through time and finds the maximum value. This filter also outputs a band of metadata called time. It shows at which time slice each positive match was found. In this case, black is the first time and white is the third. If you opened this in a proper NetCDF viewing tool, you would see the actual date stored in the pixels. We can also use this to filter other bands. For example, this is a selection of band 3 from the times identified as wet. Some sockets allow multiple bands to be connected at once. The data flows through the system as vectors and is eventually written to the output as separate bands. For convenience, new aggregate bands can be created on the input dataset. This is equivalent to wiring up multiple connections, but allows datasets with a great many bands to be operated on with ease. New bands are specified using regular expressions. This one will match all bands that begin with a capital B. This panel shows the XML. This is the query that is sent to the server when the snapshot button is pressed. Until now, we have only run the query on a small portion of data, but if we copy the text, we can run over the full dataset, either all at once or tile by tile on a high-performance computer. This is the metadata of the input dataset. Take note of the attributes and data types of the bands. There are 3 time slices and 2 spatial tiles, each 5000 by 5000 pixels. The spatial extents of the dataset do not cover the whole image, so the exported region will end up being smaller than this. We can make some changes to the query before running it. Let's query a higher resolution dataset. This query traverses time first, so it's worth adjusting the cache settings to favor that dimension. Finally, we'll write the reduced output of the less than filter to the output as well. The query is now ready to run. The output is a regular netcdf file, which can be loaded in standard viewing tools. This is the wet band. This is band 5, infrared. These are bands 4 and 3. Future versions will have better capability for band naming. And this is the time band. You can see the date value of each pixel at the bottom of the window. This is the header of the output file. Notice that metadata has been passed through the system. Some attributes, such as the fill value and data type, are modified automatically by the filters. This can be overridden in the query XML if desired. We hope you have enjoyed this brief demonstration of the Raster Storage Archive. You can download the source code from github.com/vpack/RSA.